Okay, so it's supposed that rabbits live forever and that every month each pair of rabbits produces a new pair of rabbits, which becomes productive at age 2 months. If we start with one newborn pair of rabbits, let AN be the number of pairs of rabbits we'll have in month N. Okay.
A little weird.
Yeah, so the idea, this is a well-known sequence. I don't know why it's so famous. It does seem to represent a lot of things. So in month 1, you have a pair, I guess, for lack of a better word, which is you have one pair. Well, maybe we should use one. In month 2, that's where I guess I'm struggling here, because it says that you produce a new pair of rabbits. So in month 2, this pair. Oh, okay. So I'm sorry. Maybe that does make sense. This pair, their age is like 1 at the end of 1 month, and then they're at the end of month 2. Their age is 2 months. And so now they can procreate. So in month 3, okay, they produce offspring. So there's this, we'll say new pair. Okay. And at the end of month 3, they are age 1 month. Okay. But then you still have the one pair that like this line stays. Let me try to grab another color here. This line will always stay through. Okay, so there's always 1, 1, 1. Okay, each month from the original pair. But then their first offspring in month 3, they're 1 month old. But then this new pair is now age 2 months here, so they are ready to reproduce. This feels like a health class. So the thing that's also going to make this more complicated is that this original pair, they can also produce yet another new offspring in month 3. So at the end of month 3, they've produced a pair. So maybe let me try something different here. I don't know if this is helping or not. So there's let's say an A and a B to start, and that's month 1. Month 2, there's an A and a B. Month 3, the AB produces a CD. Okay, and then month 4, that CD still exists. Okay, AB is still there in month 3, but they can also produce a new EF. And they're also there in month 4. Okay, so now we do some totals. So the totals are 1, 1, 2, or not totals, individual, like by month. So this is like column total, and then this is 3, and then the total is, or the overall total is now 1, 2, because you're adding the previous one. So now there's 4, and then there's 7. Is that would actually, we don't even need that. That's not what they're asking for. They're not asking for a sum. So in month 5, okay, month 5, CD still exists. Okay. But they now actually produce, because they're 2 months old, they produce a new pair. So we'll call that, we got to change kind of denote here. Let's go alpha, beta. Okay. And AB still exists. Okay. EF, they can't reproduce yet. Okay. But AB can also produce a new offspring themselves. So they'll call them GH. So this now produces 5. So when it says it may help you to draw a picture.
Mhm.
That's they're looking for some sort of like indicator of what's going on here. And I do think this actually shows it with the arrows. Or something like this. And there's also like, if you just Google rabbits Fibonacci, you'll get lots of pictures that are better than this. Okay.
Alright.
And then we need to explain why this works. Let me know when I can move past this.
Yeah, you're good.
Okay, sorry. Sometimes I just don't know. So the Fibonacci sequence says AN equals, well, I'll use their notation. FN equals FN minus 1 plus FN minus 2 for n greater than or equal to 3. What that means is you take the previous two and add them up, which means you need to be given 2 of them. So F3 equals F2 plus F1, which is 1 plus 1 equals 2. Is that what F3 is? Yes. F4 is F3 plus F2, which is 2 plus 1, which is 3. Yes, that works. F5 is F4 plus F3, which equals 3 plus 2, which is 5. And these all match up.
Right.
So what I would do is I would show this right here, the Fibonacci sequence right here. And then I would also diagram the rabbits somehow, indicating reproductive paths, things like
Okay.
that. Okay.
Yeah, it's asking explain why. Okay.
Yeah. So the explain why feels like it's the picture.
Right.
And you say that like the original pair can't reproduce until the end of month 2, but then they reproduce every month thereafter. The reproductive pair that they produce can't reproduce until month 5, which is when you see a new group there.
Right.
And then, EF continues, and you want to show enough. And I think 5 is enough to kind of demonstrate like your understanding of this.
Okay. Alrighty.
Do you feel like there's enough here to answer this first part?
Yeah, if you just write like a little sentence.
Sure. Let me type it. I've been let me just type it in another thing and then I'll
Okay.
copy it in. Did you raise any animals growing up?
I did not.
Yeah. I assume this is more interesting if you grew up on a farm.
Right.
All right, so here again, this is not great English, not my specialty. I do write well, but not quickly. But you can
It's all good.
you can go something like this. If you want to if you want to have some bonus points here with your instructor, you might ask if it's reasonable for rabbits to reproduce indefinitely. Because as you saw, AB just continues to reproduce. And that, that's not realistic. I mean,
Right. So just drawing that picture and then
yeah,
describing it should be
yes.
alrighty. Should I also write out the Fibonacci sequence as well with it?
Yes, I would include all this. I
Okay,
would maybe
yeah.
include this first and then some sort of diagram and then some words to go with it.
Okay. Alrighty. I'm good to move on.
Okay. Okay, so the next part is to show something. Okay, suppose that Bn equals f of n plus 1 over Fn. So that's the terms. And then it says to show that Bn minus 1 equals 1 plus Bn minus 2. Okay. So how to do this? And it says to use asterisk, double asterisk, then asterisk. Okay. So let's start with double asterisk. Bn equals Fn plus 1 over Fn. And we're from a previous line, we know that Fn equals Fn minus 2 plus Fn minus 1. Is that okay?
Yep.
Although they're using kind of this odd notation. So it's almost like, so there's variations on this. Like you could say Fn plus 1 equals Fn minus 1 plus Fn.
Mhm.
So okay, so I think, so what they're trying to do is play around with like cancellations. So it's like Bn equals Fn over Fn plus 1 over Fn.
Mhm.
And then that produces the 1. So we'd want to somehow, I don't know about this discussion here quite yet. We'll see. You want to say that they cancel like terms or divide each, something like that,
Yeah.
plus 1 over Fn. And so Fn, we could write Fn as any of these combinations here, but that doesn't seem to equal what they want here. Like I can't just put an Fn minus 2, Fn minus 1 down here because they want Bn minus 2. So what to do? So this is Bn minus 1. I have no idea. I'm gonna search the internet and see if this
Okay.
is a thing that has been determined before.
Yeah, because I looked at it and I was like, I don't even know where to start.
It's some sort of like thing where you just move some things around and you get the right indexing and then it works. So okay, let me try something different. This didn't go down the right path. All right, so they want you to start with this. So Bn equals Fn plus 1. Oh, I'm sorry. That is why it didn't work, because that's in the subscript. That's silly of me. Okay, so Bn minus 1 means wherever you see an n, replace with n minus 1. So the way that works is you get Bn minus 1 equals Fn minus 1 plus 1 over Fn minus 1. All I'm doing is putting n minus 1 wherever I see an n, like
Right.
that. And so that produces Fn over Fn minus 1. Okay. Not great, but let's just see what we got here. So Fn is equal to Fn minus 2 plus Fn minus 1. That's the asterisk. That's the given in the first part of the problem. So this equals, so now I'm taking this right here, Fn minus 2 plus Fn minus 1, dividing it by Fn minus 1. So again, just taking that, substituting. So now you can actually divide both of these by Fn minus 1. So on the right, it goes to 1. So that gives us the 1 that we're looking for. So this part is the 1. So it's plus Fn minus 2 over Fn minus 1. And this is where I got to go back and like actually figure out what do they actually want. They want Bn. They want Bn minus 2. So Bn equals Fn plus 1 over Fn. So for Bn minus 2, let's do the same. Let's go n goes to n minus 2. So that means Bn minus 2 is your new subscript equals Fn minus 2 plus 1 over Fn minus 2. So your Bn minus 2 equals Fn minus 1 over Fn minus 2. And if you solve this for Fn minus 2, I think that's what we want, or Fn minus 1. Yeah, let's solve it for Fn minus 1. You get Fn minus 1 equals Bn minus 2 times Fn minus 2. And this right here, you substitute right there, and you get something nice. You get a bunch of cancellations. You get Bn minus 2, Fn minus 2, and you can see you get a cancellation there. There it is.
Wow.
That worked.
That was a whole bunch of just stuff.
Yes.
So what was the point of doing that?
So there's this like whole world of math where you rewrite recursive sequences to make them more simplistic.
Uh-huh.
So imagine you were writing a program to do this. If you did it directly, you have to do like a calculation and then another calculation. And let's just say there's two calculations. Well, and this is very simplistic. We've brought it down to one calculation.
Uh-huh.
Is it for us, like we don't care? You can make the argument that with processing power being what it is, who cares? But these things actually do matter. I was watching a documentary last night, and when people first started using email, most of the control servers overheated because it was just too much going on. So if you can cut down on like throughput, this was like 40 years ago, but same thing applies now. If you're doing a lot of calculations, if you can reduce any part of it, you do that to optimize it.
Okay. To show that all n is greater than 3.
That's all incorporated into this.
Oh,
I mean, that's already been, that's just, they can just say to show, and they don't even need to say that because this is only defined for n greater than or equal to 3, but it's implied.
Okay. All right. So that's just like I'm just trying to understand like just the reasoning behind why students do that.
I don't know. So
is it like a proof for something?
Okay, so well, let me tell you the real reason. So you're about to move to what are called you maybe already done this, like power series.
Yeah, we're doing a bunch of
something like that, power series like that. n equals 1 to infinity. So you can do some things to
Or
these.
what do teachers call it? P series?
P series is one of them, but
Okay,
the power series
that's separate.
is 1 plus x to the 1 over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus so on.
Oh, so it's a different thing.
It's a different thing. P series is 1 over x to the p converges for p greater than 1.
Okay, I didn't know if it was
Yeah.
P series was shortened for it or something.
So this thing right here is sigma x to the n minus 1 over n minus 1 factorial from n equals 1 to infinity. Or it's sigma x to the n over n factorial n equals 0 to infinity. Which is better? The one on the right, because it's like it's more compact. And that's kind of what we're doing here, kind of. So it's like manipulating these indices to make things like nicer.
Okay.
There is value in this. It's one of those things you almost, I don't want to, you'll see it in class and you hopefully will be awed by some of the importance of this, but
Okay. Yeah, because we haven't seen any of that.
yeah, it's coming. It's, chapter 10 or something.
Oh, really?
Chapter 9, or I don't know, 9, 10, out of somewhere in there.
Yeah, we're like mid chapter. We're at 8.4 right now.
Okay.
All right, I'm ready to move on to
Ready for 3. All right. Ready for 3. I'm not. I gotta figure out what this wants. These are okay. Assume that Bn converges to some limit L. So Bn is, we got to go back and grab it. Bn is Fn plus 1 over Fn, and it converges to some limit L. And we want to use triple asterisk. So triple asterisk was, so there's Bn. Triple asterisk was Bn minus 1 equals 1 plus 1 over Bn minus 2. Define the limit L. Okay. So the Fibonacci sequence, maybe we just start out here. 1, comma 1, comma 2, comma 3, comma 5, comma 8, comma 13, comma 21, and so on. So this goes on obviously forever. So this Bn is the ratio between numbers. It's like, so for our purposes, like the first one is like 1 over 1, then 2 over 1, then 3 over 2, then 5 over 3, and then 8 over 5, 13 over 8, 21 over 13, and so on. And they're saying that this converges to a known value. Is that okay? Like, is that clear, like what it's asking for? Like these numbers, like the first one is 1, then it's 2, then it's 1.5, then it's 1 2/3, and then it's 1.6, and like this goes on, but it like eventually reaches this like L, the golden ratio, which maybe you've heard before.
No,
And we have to figure this out. So the golden ratio is this like ideal ratio between lengths of sides.
okay.
And like a lot of things that when you say so, oh, like that looks right or doesn't look right, sometimes you're referring to this golden ratio. So the golden ratio is 1 plus the square root of 5 over 2. And that's so somehow this thing produces that, which I still don't have a nice so let's just look for something. See if we can get there. Not helpful.
Is it not just like as simple as just taking the limit of bn minus one?
So it says that, but I mean, I don't know how to find the limit of this thing. So,
Okay. Right.
um,
Yeah. Okay. I understand.
so and then they say to like use this to do that. So what I found here is that they somehow, and then this is the part we've got to figure out. Somehow, like something that we do breaks down to the following: x equals x plus 1 over x. And when you solve this, which we're going to do real quick, x squared, move the x over, minus x, minus 1 equals 0. When you solve this using the quadratic formula, you get 1 plus or minus the square root of minus 1 squared minus 4 times a times b all over 2a. You get 1 plus or minus, this inside here becomes the square root of 5 over 2. And when you subtract, you get a negative number. So it just leads you to 1 plus the square root of 5 over 2. And this is the golden ratio, as I wrote above. So what I'm trying to do is fill in the gap here. We need to somehow like get to this, which I think is what is trying to be shown here. Like somehow we get something like this. Really struggling to figure this out. But let me give it a look here a little more.
Okay.
See if we can find this. Okay, so Bn, go back. Bn is Fn plus 1 over Fn, and then Bn minus 1 is 1 plus 1 over Bn minus 2. So we could maybe rewrite this to Bn minus 2 plus 1 over Bn minus 2. And that is kind of, it's kind of this, kind of.
Right.
Somehow we got to make the relationship. So if we change this here to Bn minus 1 equals Fn over F minus 1, I think we did that earlier. What we could do with that is make this Fn over Fn minus 1, and then Bn minus 2 would be Fn minus 2. No, Fn minus 1 over Fn minus 2. Is that right? Yeah. So that would lead us to Fn minus 1 over Fn minus 2 plus 1 over Fn minus 1 over Fn minus 2. We don't think we're going to get this, but let's see. So this becomes Fn minus 1 plus Fn minus 2 over that, but that cancels Fn minus 1. All we did is prove the Fibonacci thing, because that just says Fn equals Fn minus 1 plus Fn minus 2. That didn't work. We seem to be on a better path over here. So the only kind of like thing that I could suggest is maybe from, I don't think this is right, but from this red line right here, this line gives us what I needed, that whole x plus 1 over x is you could somehow say that bn minus 2, somehow you'd have to convince yourself that bn minus 1 is really equal to bn minus 2, which isn't true at all. It is when n equals 2, I'm sorry, 3, when n equals 3, this is true, I think.
It doesn't it? It n is greater than or equal to 3, so isn't it? True.
Yeah. So it's like you could maybe do something there. So like what I'm trying to say is like this part right here leads to like everything here leads to back to this equation right there. We're back to the previous line here. And then you solve that, and this is the golden ratio. I don't know where else to go here is the truth.
Well, I mean, that does work. Gets us
Yeah,
where we need to be.
it's a hack. I mean, it's not like a
I mean, it's the best we've got so far.
yeah. I'm rarely stumped, but this one, because I don't have any context, I am truly stumped by what they are
Yeah,
asking.
I was looking at it. I just didn't even know.
It does have to do with the indices. If there's office hours, maybe go. Make sure you show that you've done the previous 2 parts, and just say, look, I know where I'm supposed to go, but I don't know how to get there.
How do we know we want to get to that equation right there?
Well, because this works. This is the golden ratio, and it comes from this equation. You can cite some online resource for that if you.
Because number 4, we're supposed to write a paragraph about it.
So there's probably everyone will use this source, but the one that I found that I think is kind of the most, I guess, worthy of this. I mean, National Geographic's a good place to go. I'll throw that in the chat here. So you've got it. National Geographic's always good. So you're looking at things like pyramids for applications of this. There's the stained glass that you may have seen that sort of gets smaller and smaller for this. See if I can find a picture of that. The kind of sometimes people talk about the relationship between like your eye level and your nose and your height of your face and width of your face. They sometimes talk about that as being a golden ratio. We've got some time left. Is there some other stuff you'd like us to go through or talk about? I can keep looking on this. I mean, I can also just try to work my way through it if you think that will be a good use of the time here.
Yeah, I mean, it's not due till Wednesday, so we can always recollect ourselves and try again tomorrow.
Let me do some more searching here, see if I get any hits on this.
But like what we did, that doesn't make sense.
Yeah. Yeah. So all right, I think I've got it here, which I don't like this, but I think I've got it here. So let me try to work through it. So the limit as n goes to infinity, fn plus 1 over fn equals L. That was somehow given somewhere. Is that okay? That was given
Right, yeah, it was. Yep.
somewhere.
Yeah, it is.
Okay. So they say start with that. They say start with this like thing. Like great. So then they off to the side say, oh yeah, fn plus 1. Well, let me do it this way. If you want fn plus 1 is the previous one plus the previous one.
Right.
So okay, we're playing this game with indices again. Okay. So you substitute in, you go fn plus fn minus 1 over fn like this.
Okay.
And then this equals the limit as n goes to infinity, fn over fn plus fn minus 1 over fn, which is equal to the limit as n goes to infinity, 1 plus limit as n goes to infinity, fn minus 1 fn. So all I did, like here, what I did, from this step to this step, I just divided and then I added the limit to this other thing on the right. And this is the next thing is very non-obvious. You flip this on the right. So it's 1 over fn over fn minus 1. And you're like, why would you do that? This is what you should be thinking. So this right here on the right is really, it's really, if you reindex it, it's 1 over fn plus 1 over fn, which is what we started with. So the way the limiting works here, depending on how much you're supposed to do, you're supposed to find the limit of the top and then the limit of the bottom. And this all equals 1 over L. And this part up here equals 1. So together it equals 1 plus 1 over L.
Okay.
And so if you go back up to our first line, what did our first line equal? It equaled L.
Right.
And so this was just a rewrite of that first line. So it becomes L. And this is that equation that I was showing you before. So you multiply everything by L squared minus L minus 1, and you solve it and you get L equals 1 plus or minus square root of 5 over 2.
That looks nice.
It did work. And I'm not gonna like claim that I understand. I'm not gonna claim that I came up with this on my own. I'm gonna send you the explanation here, but do not copy it because it uses different indices than you're using. It uses capital letters. It'll be a very like clear violation of some thing you probably agreed to. But what you're doing is you're saying this is known. This is like on the left side of the equal sign, and this is on the right side of the equal sign.
Right.
And then you work out the right side all the way down like we did. And then you say, oh yeah, it's this. And then you set it equal to the previous one. And then it works.
Nice. Yeah, I think number 3, we got number 3 down.
Yes.
That's a good enough explanation. Can you scroll up like to number 2 where we worked that one out?
Absolutely. Where do you want me to?
could you just like give a like a step-by-step kind of thing, just like a little summary, just even like just a couple words for each step, just to kind of.
All right, so this is where we started here. Let me do it in blue, different color here. We started here, and then we went here, and what we did is we re-indexed, basically using this right here. We went from n to n minus 1.
Okay.
And that was our result. We then substituted this right here in there to get a new numerator.
Right.
So that new numerator we split apart. And then we just reduced. I think I have an indexing problem somewhere. Oh no, I reduced this one over here. And then we got kind of stuck. We got kind of stuck right here. We're like, well, what do we do? So I went back to BN. I went back to the definition. And I said, well, let's just try putting n instead of n minus 2. So like n minus 2 went there. It went there for that n, and it went there for that n. And we just basically re-indexed again. You re-indexed to get something nice. And then we realized like a lot of the stuff in this line right here was over here. So we solved for fn minus 1. We solved for that by just moving that over. And then we substituted that solve for line into the denominator, which was right down here. And then we just canceled terms.
Okay. All righty.
And that does it. Like it
All right.
amazingly works out, which I wouldn't have expected. So
this project was not nice and easy like the other ones.
No.
But yeah, we got everything, I guess.
Sounds good. I will send you the notes here shortly in the next few minutes, and I'll see you next time, whatever that is.
All right, appreciate
All right, thanks, Trenton. Have a great day. Bye now.